Hi again, I'm Haipan. So I'm going to present this open problem with Alec, John, and Rob from MSR, and Akshay from UMass. And it's about getting fancier regret bounds for contextual benders. So as I mentioned in my last talk, Microsoft is using contextual benders in real products. So contextual benders are useful stuff, and we therefore want to design more adaptive, robust, and more practical algorithms for this problem. And so how do people design a more adaptive online learning algorithm in theory? Well, one way to do it is to just think about more adaptive regret bounds. So if you look at full information setting, people have studied many different kinds of adaptive regret bounds, like small loss bounds, variation bounds, path bounds, etc. And even if you look at just the classic multi-arm benders, in recent years, people have also shown small loss bounds, variation bounds are possible. But there's very little study for contextual benders. So we thought we started from the simplest and asked whether small loss bounds, aka first order bounds, are possible for contextual benders. So that's the question, and to show you exactly what I mean, let me introduce some background. So again, we have X, which is an arbitrary context space, and we have K actions or arms, and the policy is a mapping from a context to an action. And you are given a set of policies, pi, which are huge cardinality n. So you don't want anything that's polynomial in n. And at each time, the environment decides a pair of context and loss vector and reveals the context to the player. And the player or the learner picks an action AT and then observes the loss of this action AT. Okay, and the regret against a fixed policy pi is just as usual. It's a difference between the loss of the player and the loss of if you could keep playing pi all the time. So we are going to consider two settings. The first one is a stochastic setting, where xt and lt they are drawn from a fixed but unknown distribution D. And naturally, the optimal policy pi star is defined as the policy with the lowest expected loss. While in the adversarial setting, xt and lt they are decided arbitrarily by an adversary. But let's say for simplicity, we consider a previous adversary, so they are decided ahead of time. And an optimal policy pi star is just the best policy in terms of the empirical loss. So a typical objective is to bound the regret against pi star by something that's sublinear in T. Okay, so the very first classic algorithm is XB4 by Auer et al. And it gets in excitation an O of root T k log n regret, which is optimal, but the algorithm is inefficient in the sense that its running time is linear in the number of policies. And to get around this computational barrier, people have been using this kind of optimization oracle, which takes as input a set of training data. So it consists of pairs of context and loss vectors, and it basically outputs the ERM on this training data. So given this oracle, an algorithm is oracle efficient if it runs in time polynomial in T, K, and log n. And this is excluding the running time of the oracle. Okay, so surprisingly, Hassan and Corinth show that even with this oracle, there's actually no oracle efficient algorithms with low regret in the most general setting. But despite this negative result, in recent years there have been many papers on getting efficient algorithms with some additional assumptions. Okay, but the point is that all these bounds, they are in terms of T, which is kind of pessimistic, and we want something that can be much better than T in some cases. So this leads to our question about getting first order bounds. So recall that we have two settings, and in both settings we are going to define something that we call the optimal cumulative loss. So for the stochastic setting, L star is just going to be T times the expected loss of pi star. And for the adversarial setting, it's just going to be the cumulative loss of pi star. And now the goal is to bound the regret to pi star by something that's sublinear in L star instead of T. Okay, so it's kind of well known and it's achievable in full information setting. You can always replace the T with L star. And it turns out that even in multi-arm bandit and even in combinatorial bandits, you can get something very similar by these papers. Okay, so we thought the first question we have is the following. So whether there's an algorithm which guarantees root L star times K times log n over delta with some minus term with probability 1 minus delta in either the adversarial or stochastic setting. So that's the first question. It's natural because I told you the optimal regret is root T K log n, and now I'm just replacing T with L star. Okay, and it turns out that the problem is surprisingly hard, and we don't even know whether there's an inefficient algorithm to get this. So we are happy. So this question is more of a information theoretic question. So we are happy if you come up with an inefficient algorithm for this problem. And let me just quickly tell you what we have tried and what are the possible results. So if you directly apply the results for multi-arm bandits to this problem, you will get the right dependence on L star, but you will have a poor dependence on the number of policies. So that's not what you want. But you can try to generalize the right algorithm for multi-arm bandits to the contextual setting. So this is the positive result that we found. If you apply the clipping trick from this paper for multi-arm bandits to the XP4 algorithm, so which is the following: you do the exponential, you maintain a weight for each policy using exponential weights. So L tilde is some importance weighted losses. And now PT of A is just the sum of the probabilities of the policies that picks A at context A XT. And the most important step is that you're going to sample AT from some clipped version of PT. So this PT tilde is going to be 0 if PT of A is smaller than some predefined threshold gamma. And otherwise, it's going to be proportional to PT of A. So that's the most important steps, and then LT tilde is just the importance weighted losses. And it turns out that we can show that the regret is going to be L star to the 2/3 with some other minus terms. So it's kind of weird because you apply this algorithm to just multi-arm bandit, you get root L star, which the thing that we want. But for the contextual bandit, the best we can prove is L star to the 2/3, and we don't know whether it's possible to get something better for this algorithm. So that's basically the first question. But based on this observation, we asked the second question, which is whether there's an oracle efficient algorithm for the stochastic setting that gets L star to 2/3 regret. Okay, and as I showed you from the last slide, this is possible information theoretically. And so we are asking for an oracle efficient algorithm. And to get around the harness results by Hassan and Coren, we only ask for the algorithm for the stochastic setting. Okay, and again, it's a surprisingly hard problem. And so we will consider solving this weaker version of this question to be some important progress, which asks for still oracle efficient algorithm, stochastic setting, but just anything that's better than root T as long as L star is smaller than T. So if you have this, then you solve this with alpha being like 3/4. So this is a weaker version of this. And what we have tried to use the clipping trick with existing algorithm, but they don't seem to work. So for every proposal we had, we always came up with a counterexample showing that they don't work. Okay, last but not least, we are offering $250 for either a positive or negative resolutions to each of the two questions I presented. So please solve it.
Okay, is there any question or comment? So I just heard from Elad Hazan that he's willing to double that price, he just told me.
Really? Oh. That's great.
So the second open problem is given by Benjamin Fish, and It's on meeting times for automata. Or we do it. You put your. Maybe I can help you. Just put it in your pocket.
Can I do that?
And let me do it.
Okay, so today I'm going to be talking about an open problem about learning random automata, and this is joint work with Lev Razin. So the question itself is incredibly simple to state, which is for one of the oldest hypothesis classes in the book, namely deterministic finite automata, specifically on n states, we want to efficiently pack-learn them. And the story for this problem, at least for the purposes of this talk, like many good stories, starts with a result of Manfred, who proved in general that the answer is no, that there are cryptographic lower bounds. And much more recently, even if we relax the problem so that instead of an arbitrary DFA, we're now just trying to learn a random DFA, where the DFA is chosen uniformly at random with random transitions and accept-reject states. The answer is still no, in the sense that it has superpolynomial statistical query dimension, so we're unlikely to find an efficient algorithm. There are query models where the answer becomes yes, but at least for PAC, we have no positive results. And when that occurs, one of the most natural things to ask for PAC is, if we can't do it for arbitrary distributions over the training examples, then let's try to do it under the uniform distribution. So that's the open problem, which we just want to efficiently pack-learn random DFAs on n states where the examples are coming from the uniform distribution. And given the simplicity of this problem, at least its statement, it's surprising to me that we have no non-trivial upper bounds or lower bounds. Even under improper PAC, where we're allowed to return any function, not just a DFA, that has low error, and in addition, we're allowed to choose the size of the input, the size of the dimension of the training examples. So even if we're allowed to choose the dimension of the training examples to be length, say, n squared, we still don't know how to do anything. And the trivial algorithm is very slow in the sense that if we just want to try every single possible DFA on n states, then there's 2 to the n log n of them. So it's not even known how to get down to just 2 to the n time. So for the remainder of this talk, I'm going to suggest one method that we believe may help get from 2 to the n log n to 2 to the n. So our approach is going to be through Boolean Fourier analysis, which I do not have time to do a full intro to, but the very fast version is, for any Boolean function, we can write it as a unique linear combination of parity functions, one parity for each subset of the input, where a parity function just says if there's an even or odd number of ones versus negative ones. And the coefficients are called the Fourier coefficients. So there they are. And the set of all of them is the Fourier spectrum. The one useful definition is that for a given collection of subsets, we'll call the Fourier spectrum epsilon concentrated on that subset if the weights that is the squared coefficients, are small on the subsets that are not in that collection. In other words, all of that weight is in that collection. And that concentration is helpful because it allows to learn under the uniform distribution. So an approach first started by Lineal and others is that if you have an algorithm that can somehow identify a collection of subsets on which your unknown function f, which in this case is a random DFA, is epsilon over 2 concentrated, then in time polynomial proportion to the size of that collection, we can pack learn under the uniform distribution. Okay, so now we've reduced a learning problem to a problem about concentration of random DFAs. In general, proving statements about concentration is difficult, so I'm going to reduce the problem yet further through what's called the ith influence. And the ith influence has a definition both in terms of concentration, but it also has a natural definition in terms of a random walk, in this case on a DFA. So if we take a uniformly random string and then we flip the ith bit, the ith influence is just the probability that the two functions on the same function on these two different strings differ. In other words, we take a random walk over this DFA. At some point, we split into two. And we keep on going. So to prove that we have a very concentrated spectrum, we're going to try to prove as many influences as we can are small, which means at the very least, we can show that this probability is small if we know that the random walk converges again. So once it splits apart, then it converges. And this is another way of saying that the meeting time is fast. That is, this flip bit won't make any difference if we end on the same state, not only on whether it's accept or reject, but the exact same state. And here's the part that we can't prove, which is, but we believe to be true. I'll skip a bunch of this notation here, but all of this is saying with high probability over the course of the choice of the DFA and the string, for any two states of your DFA, you're going to land back in the same state within n steps, order n steps. And this immediately gives us a learning algorithm. Namely that if this conjecture is true, there's a 2 to the n time learning algorithm for random DFAs under the uniform distribution. As long as your examples are length at least order n, and your error only needs to be 1 over poly n. And the idea for getting from the conjecture to the result is that if we take any ith influence, except for the last O of n of them, then over the course of this random walk, we're going to converge again, and then that influence is going to be small, which means all of the weight must be concentrated on the last O of n indices. And we do have some experiments indicating that the expected meeting time is not only order n, but exactly n in this case. Unfortunately, because there are 2 to the n log n DFAs, it's hard to even run experiments to get high probability results on meeting times, rather than, which is what we need, rather than expected meeting time. So we have a bunch of open questions, which is, first of all, we've reduced this problem to a question about meeting times on random DFAs, but we don't know if it's true. But even if it's not true, we've used this notion of the ith influence to reduce a statement about concentration of the Fourier spectrum of random DFAs to a question about random walks. So I'd love to know if there are other reductions of that type where we can take a statement about concentration and move it to something that's maybe easier to work with. And finally, this was all just to get from 2 to the n log n to 2 to the n. So getting further than that, or if it's impossible and there are lower bounds, none of these things we know. So unfortunately, because I'm a poor grad student, I can't offer a $250 prize.
But same thing ELAD can.
But
and will.
I can at least promise that this problem is interesting and elegant. And in conclusion, please send help.